It's a great pleasure to introduce Shivakant Gopi. So Gopi is a PhD student at Princeton University under Zeev Dvir. He has done a number of major contributions to the theory of error correcting codes, incidence geometry, and related areas. And he won Best Paper at Stock 2015 for one of his results. He has been an intern in our lab about a year and a half ago, and then a visitor. And now he will talk about some of his recent results. Thank you.
Thank you very much, Sergey. So I'll talk about, thanks for coming to the talk so early in the morning. So I'll talk about maximally recoverable local reconstruction codes. These are codes for distributed storage applications. And this is joint work with Venkat Guruswamy and Sergey Ekinen. Most of this work was done when I was an intern here and when I visited MSR Redmond. Okay, so let me start. So let's start the question, how big is the cloud? Like, how much data do you think is stored in the cloud in the world? Any guess?
Exabytes.
Yeah, exabytes is right order. Like, it's in fact like a few hundred exabytes is the right order of magnitude. That's like, and 1 exabyte is like 10 to the 6 terabytes, a million terabytes. And these are stored in like this is how the cloud actually looks like. It's this gigantic data centers where they keep all the servers. They cool them down. And all this data in the cloud, it's ready to be accessed, all these exabytes of data. And this has been increasing exponentially year on year. And it's not cheap. The cost to maintain all these data centers and store all this data runs into tens of billions of dollars. A lot of electricity is consumed by these data centers to cool and run all these servers, right? So how is this data stored? So data is typically partitioned. All this huge amount of data is partitioned into small parts, and each part is stored in an individual server. So typically, each server has a capacity of a few terabytes, and this is called distributed storage. You break it up into small parts. And the main problem is, okay, so all this data is in the cloud, and when a user wants some data, he just makes a request, and you want to give the data to him. Let's say he opens his Facebook page, and he wants to look at some picture from like 3 years ago. You want to retrieve that picture in like a few seconds and give it to him. So you want to do this really quick, but sometimes what happens is the server doesn't respond. There can be several reasons. Maybe the server which has the data is rebooting at the time, or maybe it's updating its OS, or maybe there are network bottlenecks, like the network to which the server is connected is just clogged with other data right at that point, or maybe the server has completely crashed sometimes. And then, we'll refer all of these things as erasures in this talk for simplicity, right? So that's the error model. So sometimes servers just gets erased, like for different reasons, and you don't want the user to know this, right? You don't want to keep him waiting for like 10 minutes for the server to like upgrade and do all this stuff. So you want the user to get what he wants immediately. So this is called recovery, right? You want to recover from these erasures or crashes. So there are two different cases. So the typical case is the user requests a small amount of data, a few megabytes, let's say, but the server doesn't respond, because maybe it's just updating, or maybe there are network bottlenecks. And that's the most frequent case, or the most typical case. This is an erasure. And the other kind of erasure which is less frequent, is a server completely crashes. Just the hard disk has like gone kaput. So it needs to be completely replaced and the data inside it restored. So these are two different cases, and we need to like take care of both of them. Okay, so how did people do it before? So the traditional, several years ago, what people did when like the scales are much smaller was just they deduplicated the data. They replicate the entire data, let's say 3 times. Like you keep it in 3 different centers, and if the first one crashes, then you access the second one. Right? So for example, if you replicate it 3 times, you can tolerate up to 2 erasures. Let's say the first copy is gone, second copy is gone, you can get it from the third copy. Right? And the good things about it is that you only need to read one server in case of an erasure. Let's say this is erased, then you only need to these two are erased, you only need to look at one server, like your data is in one server. So it's pretty fast. And there is no encoding or decoding or anything like that. There are no you don't need to read this and compute something to get what the user wants. You just read it and send it, right? So there is no encoding. It's very fast. But the bad thing about it is that it's very inefficient, right? You're using 3 times the cost. And if it's like $1 billion to run a data center, all your data centers, you don't want to spend $3 billion.
Why can't I do twice?
So people this is like the unlikely scenario. Let's say both are gone, then you don't want lose the data completely, right?
So 2 servers can crash with non-trivial probability.
Yeah, it can happen. I think 3 was also it's not just crash, as I said. There can also be network bottlenecks and other things. So typically they assume that if you have a system, 2 things can fail with still non-trivial probability. But even 2 times, if do it, it's still 2 times the cost. It's still pretty inefficient. You want to do something better. So what people did instead was to use classical error correcting codes, the most famous one being the Reed-Solomon code. So how does this work? It's called a K plus H. What that means is there are K data symbols, and think of each one as one server, right? X1 to Xk, this is your data. What you do is you add an H other servers, which are functions of the data, right? So there are K things, you add some H extra servers. These P1, let's say it's the sum of the first K. The P2 is the sum with some coefficients and so on. These are all linear functions. And the property you have is that you can recover from any H erasures. So you added this H extra thing so that, let's say, any H of them are erased, you should still be able to recover the entire data, whatever is lost. And this is information theoretically optimal. So the storage efficiency is 1 plus H over K. That's the storage cost you're paying to tolerate H erasures. Think of H as a constant, typically H is 2 or 3, right? And if you want the storage cost to go to 1, if you want to be very efficient, typically you need to take K large. Let's say H is 2. To get 1.2 efficiency, you need to take K to be 10, right? And the other thing is that the field size you need for these codes is also pretty small. It's of the order of K plus H. So the field size is linear in the number of servers, and because of that, the encoding and decoding time is also pretty fast. Let's say there is a crash, you need to decode, so the encoding and decoding time are very sensitive to the field size, right? Because you need to do a lot of finite field arithmetic, and there are specialized hardware to do this finite field arithmetic, and they only work well if the field size is really small, like a byte or 2 bytes at most.
So the H erasures can happen across
anywhere, including the parity things or yeah, it can happen anywhere, either data or the parities also. Okay, so these are all good things about it. It's very efficient, and also what's the bad thing? So the bad thing is that let's say there is one erasure. Let's say X1 is erased. That the user wants to read something from the first server, but it's not responding. And you want to reconstruct it. The bad thing about these codes is that to even reconstruct one lost server, you need to read K other servers, right? And if K is 10, you don't want to read 10 servers to answer a small request. It'll take a lot of time. So this is the bad thing. That's why people cannot. So as I said, you get very good efficiency as K becomes larger and larger. But as K becomes larger, you have this disadvantage that you need this recovery is not very fast. So people cannot scale this K large. Typically, they limit themselves to K being 6 or something like that. That's why you cannot get very good efficiency because of this constraint. Okay, so what do we want instead is what we call locality. What does this mean? You want that in the typical case of a single crash, you want to recover it quickly from reading a small number of other servers. Let's call it R. So we call it, the code has locality R. If to recover an erased server, you only need to read from R other servers. Okay. So for example, look at this code. So this is there's 3 data symbols, x1, x2, x3, and there's x1 plus x2 and x1 plus x2 plus x3 are the parity checks that you added. Now let's say, and I claim that this code has locality 2 to recover any erased coordinate. So let's say I erase x1. If I erase x1, then I can recover it by reading x2 and x1 plus x2 and taking the difference. Let's say I erase x3, then I can read these 2 parity checks, x1 plus x2 and x1 plus x2 plus x3 to get back x3. And similarly, even if let's say I remove the last parity check, I can read this x1 plus x2 and x3 to get that, and so on. So this has locality too. So no matter what crashes, I only need to read two other things. So people have studied codes like this with locality, and these are called locally decodable codes. These are first formally defined by Katz and Trevisan in 2000, but informally they have been there since 1990s. They played a big role in the PCP theorem and so on. So they have very good locality. They have much stronger property. They have locality, like a constant locality, even when a constant fraction of coordinates are erased. Right? Here we're asking that only when one crash happens, we want locality, but they have much stronger property. Even if I remove a 10% of the servers, I can recover any lost coordinate by reading only 10 other live servers, like servers which are not corrupted. But because of the strong property, we need to pay a lot of cost. They need a lot of redundancy. Typically, this h should be like at least a polynomial in k, like k squared or k to 1.5 to get any non-trivial things. And sometimes, like if you want locality 2, this h should be exponential in k. So you need to add an exponential number of servers to get this locality 2 for a constant fraction of coordinates. So this is an overkill. We don't really want to do that. So what do we want to do? Instead, we want to do something which is a very famous system design principle. It's called separating normal and worst case. It was described by Butler Lamson in his famous write-up, which he called Hints for Computer System Design, where he wrote down a bunch of design principles that a good computer system designer should know. And one of the hints in that is this, that I quote him, handle normal and worst cases separately as a rule because the requirements for the two are quite different. So you want your design your system to be fast in the normal case and still be okay in the worst case, right? So you want to design these two conditions separately. So for us, the normal case, or the most common case that happens, is just a single erasure, right? This is the most common scenario, and we want good locality here. We want to answer user requests pretty fast, either a single erasure or, let's say, a small constant number of erasures. But in the worst case, we still want to protect against a large number of crashes. Like some catastrophic thing happens, we still don't want to lose our data, but we can give up locality here. I don't care if it's slow, you just don't lose my data. But in the common case, I want it to be fast. Okay, so we will design our code to handle these two cases separately. And that's what we'll do. So what do we want?
Just to clarify, you still want a single code.
Yeah, I want a single code, right? Which has both the properties. I need to protect against a large number of errors, and still I want good locality when the small number of erasures happen. Right? I want a code with both those properties. That's correct. So to summarize, what do we want? We want a code which is efficient, like we want low storage overhead. This is the whole point. Otherwise, we could use replication. And we want reliability in the worst case. So you should be able to recover from as many erasure patterns as possible. But this can be slow. And in the normal case, or in the typical case, we want fast recovery. And that fast recovery is captured by this locality, like how many servers do we need to read in case of a single erasure. Okay. So there is an alternative line of work where they look at this thing called bandwidth, how much data is transferred to recover a single server. But for us, as I said, the frequent case is the user requests a really small amount of data. It's not like a complete crash. There, you don't need to read much data from each server. So the bottleneck is the number of servers you read and not the data you read from each server. Okay, so locality is the right notion to study in this case, not the total data that you transfer. Okay, and the other thing which is very important is that you want your codes to have small field size, typically a byte or 2 bytes. This is because the encoding and decoding time involves finite field arithmetic, and that is very sensitive to the field size.
So can you actually clarify how sensitive it is? For example, if my field size increases from like 2 bytes to 4 bytes, how much I suffer? Like from 4 bytes to 8 bytes?
As I said, there's like specialized hardware which is super optimized for, like, let's say, bite-sized fields. Maybe Sergey can.
So specialized hardware, I mean, then you might not actually feel that much of a difference. But you want to run it in data centers with the current deployed hardware on a CPU. So yeah, I mean, the running time. I mean, then there are kind of people do a lot of optimizations, but my understanding is it's quadratic presumably. So if you think of the difference, And from talking to engineers, I mean, 1 byte, they say that they see no slowdown compared to almost reading data. And 2 bytes, they kind of, they green, but they might accept beyond it. They just think it's
Beyond that, you need specialized hardware.
Yeah, but yes.
But you don't, yeah.
But you don't have it locally. If you want to deploy it at scale and all your servers, you just don't have it.
Also, is it true that like Intel CPUs have actually instructions for finite field stuff?
They have it not for finite field stuff. They have some instructions that you can kind of tweak and try to, but not for everything. So, yeah.
Right. Because like, yeah, it should be roughly quadratic because they're like multiplying 2 field elements is like making a linear transformation.
Fourier transform, but
Right? Yeah, but
not for
not for like, yeah. Yeah. And another thing is that you want these fields to have characteristic too, because you want like bits. But at least the addition is just bit XOR if it's characteristic 2 fields. That's another nice thing that you want in these codes. Okay, so how do we get locality? We said we want locality in the typical case when a single crash happens. So how do we get? So we first added this H extra things, let's say, to protect against worst case erasures. But the problem with this the read Solomon codes was that in case of a single crash, we needed to read a lot of other things. So what do? We add a local parity check server for every group of size R. So what that means is, let's say you group all the servers into groups of size R. And for the first R things, you add a server which has the sum of the first R. And the next R things, you add a server which contains the sum of the next R, and so on. So you added these local parity check servers for each group of size R. So now you have locality, what you want, because let's say a single erasure happens. Let's say x2 is erased, and you want to get it. You don't need to read everything. You just need to read what is there in this local group. You will read L1 and the rest of the things in the same group, and you get back x2. Okay, so you get locality R. That's where, in case of a single crash. So that's good. So what else do we want from this code? But we still have a lot of choice, freedom in this choosing, like what is the coefficients of the linear equations P1 to PH, like what is this is something we can choose. And also you can choose, like if it's not just simple sum, you can choose the coefficients in L1 to LK. So how do we choose these coefficients? So what we want is, as I said, in the other case, in the worst case, we want maximal reliability. So what does this mean? So we want to ask the question, given this code topology, like this is how, suppose I tell you that this is how it should look like, and I ask you to choose the coefficients, then I ask, choosing different coefficients will lead you to correct different erasure patterns. Right, like choosing some coefficients will make you will allow you to correct some erasure pattern, but maybe something not, and some other way of choosing will let you correct some other erasure patterns. So let's first ask what erasure patterns are even recoverable and possibly. Like, is there some way to set the coefficients so that pattern is recoverable? And we ask what patterns are recoverable, and then let's be greedy, and I want to say that if something is correctable or recoverable, then I want to recover all of them. Like, is there a way to set the coefficient so that I can recover all the possible erasure patterns? It turns out that the possible patterns which are recoverable are just these things. So given this topology, the things that are recoverable are 1 crash in each local group plus H more anywhere. Right? These are the only things in principle that you can possibly do. And I want to be greedy, and I ask that I want to recover all these patterns. Right? So I'll maybe come back to say why this is the only things that you can possibly correct. There is a precise mathematical way to see why, like what patterns are correctable and what patterns are not. But believe me, for now, that these are the patterns that are correctable. So I want to be greedy and correct all such things. So let's define these codes formally. So there are lots of parameters, so please stop me if something is not clear. So it took me a day or two to even for me to understand this definition when Sergey first explained me. So I don't I don't expect you to understand all the parameters immediately, but I'll try to put this picture in every slide just for you to remember what parameter is what. Okay, so there are a lot of parameters. So NRHAQ, maximally recoverable local reconstruction code. It's a linear code of length n. What that means is the total number of servers, like including the parity checks and the local checks, is n. N is the total number, and R is a locality or the size of each local group. So this thing is called a local group. What that means is you first take the first R minus A, things, and then, so the way the code is constructed is you first have your data x1 to xk, you add this h global parity checks, which depend on all x1 to xk. And once you complete this, you finally add these local checks. But previously we added only one. But let's say I want to have locality in A crashes. So what I do is I add A local parity checks for each local group. So in the first, I group them into groups of size r minus A, take the first r minus A, and then compute this A parity checks for them. Right? So this L1 to LA only depend on the first r minus A, and the next two L's depend on the next r minus A, and so on. Right? So this is the code topology. So this A is the number of local parity checks in each local group. R is the size of each local group. There are r minus A here and A here. And this H is the number of global parity checks that I add. So these are the parameters. What do we want from this? So as I said, each local group has size R. If only A crashes happen in a local group, this group, then I should be able to recover the group locally without reading anything else, right? Because I have A parity checks in this local group. If there are, let's say, A things which crash here, then I should, from these parity equations, I should be able to compute whatever is lost locally. So this is, so I have locality in term A, whenever A crashes happen. Think of A as constant. But what patterns are correctable? The correctable patterns are A crashes per local group plus H anywhere else. So first you corrupt any A in each local group, and after that you can choose H anywhere and crash them. And I can still recover the entire data. Okay, so these are all the correctable patterns, and I want to correct all of them. So this is called, and Q is the size of the finite field that I need to instantiate this code. Okay, so that's the thing. So
are those P1 to PH generated the same way, like they are in Reed-Solomon codes?
Yeah, you can think of them as well. I mean, it need not be Reed-Solomon, but there'll be some linear equations in x1 to xk, but it's not clear it should be Reed-Solomon.
So the difficulty is that these H additional failures can be among this...
yeah, it can be anywhere.
Like bottom row, if it would be granted to be in the top row, then it's a trivial problem, right?
It's not trivial. Still.
But why can't you just do Reed-Solomon code and then in each group just do whatever corrects are failures? So then you first recover the top row, and then in the top row you...
No, because when you do the local, you place originally a local group, they can well go on the top row as well. Right? So you have to decode all this thing jointly. You cannot do it repeatedly.
Okay.
So I mean, even
So
these things can be corrupted.
All A plus H could be from one local group.
Yeah, it can be happening.
Worst
Oh,
case?
okay.
That's not the worst case.
What is the worst case?
So it's not clear what is the worst case, right? It can be that, like, let's say in each local group, A of them are corrupted, and the H extra ones maybe are distributed across different things, or maybe it can all happen in the same things. Anything can happen, and we want to correct all of them.
Like intuitively, what is the most kind of
so
critical
intuitively-
case to recover from?
Okay, so intuitively, it's a balance between the things. I think if you just want to recover from... Okay, so as we'll see, I will show a lower bound finally on the field size, and the difficulty comes because of these two extremes. When you want to protect your data when all the H extra things happen in the same group, but you also want to protect your data when H things happen in different groups. And these two constraints together will make what makes this problem hard. Okay, so I'll probably hopefully say it in the lower bound. Okay, so let's
Going back, is it an overkill a little bit? Can
that you
say
want to correct all these things.
that you can have both A crashes per local group and H at the same time? Instead of and, if you say or, does it make the problem maximum?
No, is it or?
You have and, right? You have A per
So, as I
group
said-
and H everywhere.
So
But it's really, what if it is or? Does it make the problem easy? You know, because from what you said, either we are in the normal case or we are in this worst case.
in the worst case, but in the worst case, like, so this H, you don't want to choose H to be much larger either. So typically in actual code, you will choose this H to be small, like 2 or 3. So your design is that, like, actually it also involves this A crashes plus this H is typically a small thing to account for the extra things.
I'm talking about the problem definition. So you're talking
Right.
about a particular solution. What if I change the problem definition to or? and you can make h larger if you want. Whatever you think is a worst case,
Right.
okay, 10%, right? So does that make the problem easier?
So you're saying that either
Either A crashes per group or H anywhere.
Right. So
it's a much easier problem.
yeah.
So, but isn't that isn't that a more isn't that what happens in reality? That either you have these small crashes or you have a huge crash. Is it likely that you have both?
Well, but in reality, the codes that are deployed are pretty short. So let's say like length under 100. So I've never heard of anything length beyond 100 being deployed. And you really care about every single redundant symbol that you place because it determines your overall redundancy. It's whether you pay 1.5x or 1.4x for all error, right? It's a humongous difference. So now you decide how many of the redundant symbols you want to place, and then you want to squeeze as much reliability as you can, and you really don't want to waste a single thing, and then you do these things. Because here, given this topology that you kind of decided on, you want to correct as much as the topology allows, and you don't want to use a single bit out of it. So you want to squeeze out everything, and then this is the definition, because how much can this topology correct? It can, in principle, it can correct all these patterns up to H per local, A per local group, and H more. And you want to get all of it, because if you are not getting all of it, this means that you are wasting some reliability that is free that you can get. So, you can over-provision and get more redundant symbols and get the same level of reliability, but then you are paying this humongous amount of money. So you would rather kind of squeeze out all the reliability that is there. That's the logic.
Right.
Yeah, it seems to me like you almost get the A crashes per local group almost for free. Like if you want this locality anyway, you have to set up these local servers, and at that point you're already getting it, so there's no need to ignore it.
Yeah, locality is it's the problem is hard because of this combination. Yeah, if you just want to correct any H values, you do the Solomon. If you want to correct local, you do the short with Solomons. But then you want to mix this together, and then it becomes hard.
Wait, so N is so what is N exactly?
N is the total number of
length
servers.
everything.
Yeah, total number of servers, including the parity checks and the local parity checks. So let me go through a small example to get the feel for it. So here, it's N is 12, which means the total number of servers are 12. Like there are 6 data symbols, 2 parity checks, 8 plus 4, it's 12. R is 6, that means each local group has size 6, the 4 plus 2, 4 plus 2. H is 2, which means there are 2 global parity checks. And A is 2 because the number of local parity checks are 2. And finally, Q is the finite field size. Okay, so what are the correctable patterns here? So we want to correct 2 crashes per local group by reading the rest of the other things in the service. So like, for example, this pattern should be correctable. There are 2 things in this group and 2 things in this group. But we also want to say that 2 things per local group plus 2 more, H more. H is 2, so you can, let's say, these curly things are the extra things, so this thing's correct, this is corrupted, and this is corrupted. Or maybe they can also happen in the same group, like this is corrupted, this is corrupted, right? So you want to correct all these patterns. Okay, in summary, so this maximally recoverable LRCs are like the most reliable codes possible once you fix the storage overhead that you are willing to pay and the required locality that you want. Right? Once you fix A, you want locality when A crashes happen, and you also say, I'm only willing to add each other extra global parities, then these are the most reliable codes possible. They correct every possible pattern that is correctable. But this is all nice, but do they even exist? Like, it's not even clear that these, like, why should there be a code which corrects every possible pattern, right? So let's quickly go through, like, I'll show you why they exist and, in fact, how we can construct them a little bit. So for this, you need to look at the parity check view. This is a dual view of codes. So right until now, I showed you how the generating view, how the code is generated, the parity checks are generated. So this is the parity check. This is the dual view. So the dual view of a code is, so as I said, a k, k plus h code is, you think of as you have k data symbols and you will generate extra h parity checks. These are linear things. But now you think of it as one block, this entire code word as just one vector. And you ask what are the h equations that these things satisfy, right? Because it has dimension k, it satisfies h linearly independent equations. these coordinates. So you write down what are the H-independent equations that all the coordinates satisfy, and that is called the parity check matrix. So any code word should satisfy all these equations. Okay. So you can specify a code by just specifying the parity check matrix. And so what does it mean to be an erasure pattern is correctable, right? So let's say this coordinate, and this coordinate are erased in your code. Okay. So then what does this mean that this pattern is correctable? So we know that this entire code satisfies this equation. This matrix times this is 0, right? So let's say you plug in some unknown variables x, y, and z here. What you get is an equation in x, y, z, which is a linear combination of this column times x plus this column times y plus this column times z is something, because you know the rest of the values, right? So you get a linear equation in these three variables. It is solvable if and only if these three columns are linearly independent, right? So that's the only way you can solve this equation. So a pattern is correctable if the corresponding columns in the parity check matrix are linearly independent. Okay? Any question? Good. So that shows us, that brings us to the parity check matrix of an MR code. This is probably the most dense slide. So I'll try to explain why. So I claim that a parity check matrix of a MR of a local reconstruction code, which looks like this, should look like this matrix here. So let me go over what these things are. So as I said, so there are these local parity checks L1 to LA, which depend only on the first R things, or like the first R. So these equations, there should be A equations which depend only on the first R variables, right? So that's why these first R variables, there are these A equations, and they're 0 everywhere else. So these A equations have support only in the first R variables. The next A parity checks will have only support in the next R variables, and so on. So these square blocks are the local parity checks. And finally, there is this huge global block. There are H equations, and these equations involve all the variables. Okay? So this is how a parity check matrix of a local reconstruction code looks like. And there are A checks, so each block has size A, width, it has number of columns is R, the number of rows in the global parity check is H, and the total length, the number of columns is the number of coordinates of the code is N. And these stars are like arbitrary elements from the finite field FQ, like some elements from FQ. So these stars, how you instantiate determines the code, like what you chose for the equations. And the rest of them should be zeros, these yellow things. Okay, so what you want is to find a parity check matrix which looks like this. This is called a topology of the code, which is just telling you that some of the coefficients should be 0 and some of them can be whatever you want. And what do we want from such a matrix? So we want maximal reliability, we wanted to correct any pattern which you can get by corrupting A in each local group plus H more. That's the same, as I said, is saying that you choose the corresponding columns in the parity check matrix. They should be linearly independent. So what it means that every minor of this matrix that you can get by selecting A columns in each local group plus H extra columns anywhere else should be full rank. Okay, so you want the stars to be such a way that this property is satisfied. So and in fact, it turns out that these are all the non-trivial minors of this matrix. So what is a non-trivial minor? Let's say you choose a minor, right? Like you choose these as many columns as there are rows. You get a square matrix. You compute its determinant. So because there are some zeros and there are some stars, either the determinant is identically 0 or it's not, right? If it's identically 0, there is no hope. No matter what stars you put, there is no way to correct this pattern. But if it's not identically 0, then there is a hope, that you, by putting some stars, like specifically from this finite field in a certain way, you can correct that pattern, right? So it turns out that only non-trivial minors are these minors, and you want to correct all of them. So these are all the correctable patterns, and you want to correct. Okay, so is this clear? Any questions? Okay, so the goal is to instantiate this matrix such that all non-trivial minors are in fact non-zero. So you could think of it as like a PIT problem, right? You have all these equations. You think of the stars as variables, indeterminates, and whenever the determinant is non-zero, is 0 identically, you cannot do anything. But if it's non-zero, as symbolically, you want it to be non-zero like when you plug in the coefficients. You want to like de-randomize this thing. So you can like, to make it, to show existence, you can just plug these coefficients randomly, right? Because we know that a non-zero polynomial, if you plug in coefficients from a large field, it'll be non-zero with high probability. So choose the non-zero coefficients randomly from FQ. Each non-trivial minor will be 0 with probability roughly 1 over Q. So, and they're like exponentially n log n, many non-trivial minors at most. So if you choose Q to be much, much bigger than that, all the non-trivial minors are non-zero with decent probability. So we know that such codes exist, or like exponential sized fields. Now the goal is to get it small and also explicit. Right? So because, as I said, large fields make encoding and decoding extremely slow. Ideally, we want a linear field size. This is why Reed-Solomon codes are so good, because they give you linear field size.
I mean, this specific code, there is no way to decode it efficiently. Random code.
Yeah. So you want an explicit code and you want small field. Yeah. I mean, once you, that's not really true, because it's just a linear code. Once the coefficient matrix is fixed, it's just solving linear equations. So.
This assumptions for errors.
I see. Okay.
You just need to solve linear equations.
So it's not recovering errors, which is much harder.
Yeah.
Okay.
Yeah.
So it's polynomial time is easy.
Easy.
Okay.
Yeah. It's like n squared, because you're just solving linear equations. But it's still it's hard because of the large field size. It takes slow. Okay, so you want explicit constructions or small size fields. So what is known about these things? The idea of locality and maximal recoverability first started with the works of Chen, Huang, and Li, this in 2007, and since then it's like been a major influence in this field. This paper has been very influential by Gopal and Huang, Schmitzi, and Sergey. A very influential paper. They first defined local reconstruction codes formally, and they studied them like systematically and see like what rate you can achieve, what are the things that you can do with them. And this MR property, this maximal reliability property, were studied by Blom, Hafner, and Hetzler for like some special cases, and they called them partial MDS codes. But in full generality, they were studied by Gopal and Huang, Jenkins, and Yakinen. They gave a very general definition of maximal recoverability, not just for this topology, for different topologies, and they also gave some explicit constructions.
For those super explicit cases, like H=1 and H=2, is there like special tricks you can do to make it, better than just the general case? Like
right. So I'll show you some constructions to the end, probably not tell you how. So as I said, so the main question here is the field size. What is the smallest field size Q such that such NR, HIQ, MR LRCs exist? That is the main question in the field. So to get an idea of what we know, so let's fix A equal to 1. So you're just adding one local parity check. Let's say H is some fixed constant, and let's say this locality, each local group has much, much smaller than n, like n to the epsilon. So random constructions are known to need n to the h, roughly, n to the h minus 1.
So in what sense they need that field size?
So if you plug in...
so basically anything smaller, random
smaller
would be bad
will be bad, yeah, with high probability. So you need you need to plug it from a large field. It's not that our union bound is bad. So this is kind of tight.
So and what was n log n before you showed like?
So that's like when h is also growing with n. So h can be at most n and a can be at most n. That's like the worst. So you can actually get something like that, n to the h.
And also, like you said initially that your field size should be small, like, and you're hoping for like your field size to be of size of order of n.
Right.
That seems too large, no? I mean, in practice.
No, n is typically like 100, let's say at most, or.
What is 100?
Yeah, and so your field size is, let's say, 8 bits, a byte. That's like 2 to the 8. 2 to the 8 is what? It's already 256, right? So you can, yeah. So you can go up to 256 servers. Right.
Okay, but if h is like 3 or 4, yeah, it's like barely more than we can handle n to h. So n to h.
Oh, so this n to the h is.
There is no upper bound like this.
There is no upper bound. It's just a lower bound.
So if there would be n to h upper bound, it would be.
Yeah, so the upper bound won't be n to the h because it will also depend on the number of local groups, right? The number of non-trivial minors will be many more than that. This is just lower bound.
Actually, okay.
Yeah.
You will be happy with n to the power of h.
Yeah, I think that's a reasonable thing.
Well, it
N to the
depends on
edge.
A and R. If you could do it for every A and every R. I mean,
Yeah.
so, I mean, like, ideally, of course, we want linear, right? We want linear for everything. If it isn't linear, then we want the lowest
Yeah.
possible.
No, but is it ruled out? I mean, can you get?
Well,
like,
yeah.
Okay.
You'll see.
Wait, sorry, why is n so small? I thought Azure has like hundreds of thousands of machines.
Right, but okay, so but the codes that I've deployed, the first code that was deployed, it was like for length 16. I mean, yeah, Azure has a lot of machines, but then when you code, you have to send data to all of these machines and you have to wait for the response.
Right,
And also you want these machines to fail independently. Like, this means that these machines should not should not share the same power supply.
I see.
And also because of how this thing is structured, you want them to be like in the same cluster, but not in the same upgrade domain. This places lots and lots of constraints. So the code that are deployed are actually very short.
Interesting. Okay. That makes sense.
So hopefully I'll get some time to at least show the results. So yeah, there are explicit constructions which give you like n to the off edge, but okay. So we, as I said, we want to get linear, and the best previous lower bound is just omega fn. So it is possible in principle to get linear. We don't know. There was a recent result by Kane, Lowett, and Rao where they showed exponential field size lower bounds for MR codes, but in a different topology. It's like a grid topology where they're like row parity checks and column parity checks, but they don't imply anything for local reconstruction codes. So this was an open problem. So what we showed, our main result was a lower bound on the field size. Right? We show that like in fact you cannot get a linear in n for every r, a, and so on. So the lower bound we get is like n times r to the minimum of a and h minus 2. It looks a bit funny. I'll try to look at some special cases to motivate why what's true. And so this is the first superlinear lower bound when r is growing. Right? When r is constant, it's linear again.
Can you remind what R is?
So r is the size of a local group, a is the number of parity checks, h is the number of global parity checks, a is the local parity.
Okay, so let me try to like sort of differentiate. So like R is growing but you initially said R wants to be small because that's the number of reads you're gonna make.
Yeah. So think of
How should I
this is so typical. You can either think of r as n to the epsilon, or you can think of r as a constant.
No, but N is also small.
Yeah, n is also small, right? So it's not clear.
No, I mean, okay. The small, like reading from 10 servers is still quite difficult, right?
Right.
I mean, but anyway, I think what you're saying is that, nice.
There should be
So
some.
what does this mean for realistic values?
Yeah,
of
actually,
NRA?
Oh, for
Do you get
realistic,
concrete numbers out of this lower bound?
that's
Interesting.
not sure.
But what you're roughly saying is that for like asymptotically, it's like n to the power of 1 plus epsilon kind of a lower bound. Because R, if you think of n to the power of epsilon, then you're saying that you can't get linear.
Right.
Nice.
Yeah, I think you get. I mean, these constants they're not huge. So yeah. So if you ask about codes of length, say 150 to 100, yeah, I mean this would be ruling out. I mean this would be like.
Yeah, but I understand. Yeah.
Giving you lower bounds that you wouldn't like. You wouldn't even probably at length 100. I mean, you would like you plug in A and H, and it would give you numbers that.
So you need field like at least 4 bytes.
Yeah, I mean, okay, I don't know, but it would be
Yeah.
telling you something that you would not see by any.
But
other
I mean, I think you
It
shouldn't
would
really
be
read.
interesting to plug in some values and
Right.
see what
Yeah.
the lower bound get out of it.
So we haven't really optimized lower bound, but also I think you shouldn't see it as like giving actual numbers. It's more like a philosophical guide, right? It's telling you that you shouldn't look for like order of n, like no matter like. Right? If we don't know this lower bound, we'll like still keep searching for like maybe there is a linear construction.
It also gives concrete nice
Yeah.
lower bounds, then it's additional bonus.
So
And
yeah,
when
there are
you
like
keep
no
searching,
really
you
horrible
just-
constants here. It's just that we haven't like looked at the concrete numbers.
When you say keep searching, you mean like that matrix you just brute force search to explicitly construct.
So that's how actually in the very initial stages you could also people brute forced
I see.
to look for these matrices. But still it's a pretty big search because if the field is already 8 bits and these matrices are huge, it's like crazy exponential search. You cannot just brute force your way through. Okay, so let's look at some other case when, like, let's say when A is approximately h and R is like n to the epsilon, then the lower bound is actually giving you n to the h, right? and the best upper bounds are like n to the h squared. So it's saying that we are not too bad. Like you cannot get linear; it should grow like something like n to the h, in some ranges at least. So we also get some upper bounds. So the upper bounds. Let me remind, the lower bound is something like this. R is the net size of the local group. So when h is 2, let's say the number of global parities are just 2, then the lower bound doesn't give you anything, right? This term, this h minus 2 is just 0, so you get just n. It's linear. So is this because our lower bound is bad, or is it actually linear? So it turns out that there is a linear construction in this special case. So this lower bound, this h minus 2 thing is actually tight. You do get a linear upper bound, or h equal to 2, and this is true for every a and for every r, right? So something like this is in fact true. Like even when r is like growing linearly with n, you do get like a linear upper bound. That's very surprising, and it's also has practical use because h equal to 2 is something that people use in practice, right? So, and this construction is very simple and very neat. This constant is also like very close to 1. So, so that's one. And there is another regime which is pretty interesting, as you are all asking, is when, let's say, you fix r, a, and h. They're all fixed constants. Again, the lower bound is omega of n, and it would be extremely interesting to get also an upper bound, which is like a linear in n when all these are constants. It would have actual practical impact. So, but that still is open. We don't know if the answer is true or not. But we've been looking at some special cases, and we found some interesting special case, like the first interesting case where h is 3 and a is 1. So it's like the lower bound is n times r, in this case, when h is 3 and a is 1. So you expect that it should grow with, and when r is linear in n, it should be n squared. But when r is constant, you should expect like maybe linear. And we do get, when r is constant, like small constant like 3, you do get something very small. Like the field size is like n to the 1 plus little 1. Right? So maybe it's true that when...
Below is as n grows.
Yeah, as n grows. It will be exponential in square root log n. Okay. And it's a very surprising construction. It comes from elliptic curves and using arithmetic progression-free sets in integers and so on. So it's not clear, like maybe there are some funky constructions which actually give linear when like all a, r, h are constants. So yeah. Okay, so my plan originally was to show you some lower bound, but unfortunately I think we're majorly out of time. But let me try to say, I don't know, a few words maybe. So this is the lower bound. We wanted to show in the special case, as I said, when h is 3 and a is 1. So shall I go till 11:30?
Yeah.
Okay. Yeah.
I'll get the room until 12. Okay, that's what I saw on the invite.
Yeah, but I don't want to.
Yeah, just.
But 11:30 is different.
Okay. Okay. So in the special case, when h is 3 and a is 1, the lower bound, this just reduces to h is 3, a is 1, so it's nr. Right? So this is the lower bound. It's already non-trivial because the previous bounds were just n. You want to get something growing with r. Okay, so how do we do this? So this is how the parity check matrix of the MR code looks like. Right? So the a is 1, this is r, h is 3, so the 3 rows here. So let's label them the columns of this global parity checks as v11, v1r. So vij is the subscript is the group number, and the superscript is just the column number. Okay. So this is how the parity check matrix looks like. So define this sets vi to be the vi is the columns of the ith local group. Okay. So this is some subset of fq, the three-dimensional fq, right? fq3, because there are 3 rows here. And define hi as just the difference set of vi with itself. So these are all pairwise differences of vectors in vi. Okay, so I'll make 2 claims about this hi. This hi is a subset of fq3. The first thing is that no 2 points in hi are multiples of each other. So these like all pairwise differences are all like in different directions. Okay, in the 3-dimensional space, and so you can think of it. So the size of the set will be r choose 2, like roughly r squared. And they all point in different directions of 3-dimensional space. So you can think of them as points in the 2-dimensional plane, 2-dimensional projective plane. This is because you can think of directions as points on the sphere, because each direction corresponds to a point on the sphere. And the sphere you can think of by cutting it open, you can think of it as a plane. That's called the projective plane. So you can think of the points in HI are points in the plane. So if you don't really understand projective planes, just think of them as points in the plane. Okay? They're just different directions in three-dimensional space. And the other property about these HIs is that if you select 3 points from 3 different HIs, then they should also be linearly independent. And if you think of them as points in the plane, this is the same as saying that the ABC in the plane, if you select from 3 different sets, they are non-collinear, right? There are 3 directions, they are 3-dimensional space, but I'm thinking of them as points on the sphere. Then 3 points are linearly independent if they don't lie on a great circle, right? And great circles are like lines in the projective plane. So 3 points in 3 different HIs are not collinear. This also implies that these HIs are mutually disjoint. Okay, so let's just believe these 2 claims. These 2 claims, you can get it from the maximal recoverable property, right? That we have that if you select 1 column in each local group plus 3 anywhere, these should be full rank. From those 2 claims, you can get these 2 things. Okay, so let's I'll skip the proof of the claim 2. I was hoping to show it, but it comes from this fact that you can correct 1 column plus local group plus 3 more. Okay, so we have these sets H1 to Hk inside this plane, and they're all disjoint, and each has size roughly r squared, and there are n over r of them. These are because they're n over r local groups. And what do we know about these things? If you take 3 different points in 3 different sets, they are non-collinear, right? This was the claim 2. And claim 1 is just saying that these are disjoint. Sorry, each has size roughly r squared. Okay, and from this we want to conclude that Q is at least nr. So how do we do this? So we use a result from point line incidences in the plane. So think of a bipartite graph between points and lines where you connect in a point and a line if the point lies on that line. This is a bipartite graph. The number of points are roughly q squared. The number of lines are also q squared in the plane. And Allen, in 86, there were a classical result. He showed that this graph is a very good vertex expander. If you take a subset of size q, much bigger than q on the left, its neighborhood expands to the whole thing, right? So if you so these are points and these are lines, the points are q squared in number, but as soon as you hit square root of that size, like roughly more than q, it expands to the whole thing. So this is what we'll use. So the proof of the lower bound is, suppose q is much smaller than nr, then the total number of points in this is n over r times r squared of all the HIs together, which is nr. So the total number of points are much bigger than q. So partition the HIs into 3 different groups, call them ABC. A is the union of the first 1/3 HIs, B is the union of the next 1/3 HIs, and so on. So the total number of points is nr, so each of them have nr over 3, which is still much bigger than q. So from Allen's result, we know that the neighborhoods expand to the whole thing, right? Each of the sets A, B, C, which are the union of the first 1/3 and the second 1/3 and third 1/3, they expand to the whole thing, which means that so this is a picture, their neighborhoods expand to the whole thing, which means there is a common intersection for all the 3 neighborhoods, right? Which means there is a line which is incident to a point in A, a point in B, and a point in C. And that is a contradiction because we know that 3 points in 3 different HIs cannot be collinear. Okay, so it ultimately comes from the fact that as soon as you hit much more than q, it expands to the whole thing. So the 3 things should have a common large neighborhood, which is like a lot of lines which are incident to a point in A and point in B and point in C. So you get a line which passes through 3 different HIs, and that gives the contradiction. Okay, that's just a flavor of the proof, and you can generalize it to like arbitrary R, arbitrary A. It's a bit more complex, but the basic idea is the same. So I wanted to show the upper bounds, but I guess I'll just keep them. It uses some like cool determinantal identities which look like this, but like a determinant of some partition matrix like this can be written as a much smaller determinant of determinants. So use algebraic identities like this to argue about the minors being non-zero. The upper bound in the other case, as I said, involves these elliptic curves. But I don't have any time to show this, and also this Bayes construction of 3 AP free sets. So there are lots of open questions. So as I said, the most interesting question is for a fixed R, H, and A, you want to get a linear field size, right? Like think of RH as constants, you want some dependence which is like linear in N. We don't know if this is true. The lower bound still doesn't rule out this, and this would be very interesting in practice as well. And some evidence towards this is our construction using elliptic curves, where R, H, A are constants, you do get nearly linear size. And in general, there are like huge gaps between upper bounds and lower bounds. So think of A and H are constants, and R is like, let's say, n to the little o1. Then the lower bound is n times R to the h, and the upper bounds are like n to the h, roughly. So this, we want to understand the dependence on R versus n, really. Okay, so let me summarize. So these MR LRCs are tailored codes for codes tailored for distributed storage applications, and they're designed so that they're fast recovery in the normal case and maximal reliability in the worst case. They have low storage overhead, and they have already been deployed in Azure and other systems. In Microsoft, they are outperforming the traditional erasure codes like Reconstruction Codes. And the main questions about this is we want small fields because they involve fast encoding and decoding. Right?
So what version is deployed?
So in 2012, the code that had been deployed had two local groups, one local parity per group and two heavy paritives, and inside the local group was 7 or 8. And then there was another deployment in 2017, but it was not announced externally, so I am happy to tell you in person. And then there is something flexible.
And what was the field size?
Yeah, it's single byte. Both ones are single byte. Yeah, and the deployment in Windows Server is actually flexible. So if you have multiple disks on a Windows Server, you can go somewhere in the settings and tell it to use these LRCs, and then it will decide itself based on the configuration of your system. It would choose the code itself and start using it. But the other code has single heavy parity, so it's just a question of which is very easy to design. So it's also single byte.
So the main question about these things are what's the smallest field size? We showed the first superlinear lower bounds, and we also, in some practical parameters of interest, we were able to get linear or near linear field size. And it would be great to get, when R, A, H are constants, to get linear field size. Thank you. Thanks.